Back by popular demand. It's the wood stove controller. You can see I've kind of finalized some mechanics on it. It's controlling it. That's the draft motor. There's the damper. Got a heat shield on it now, and a little fan. There's the controller. Right now it's running autonomously, which means I don't have the remote powered up, but it is controlling the stove. So, a number of my viewers have requested to have a look at the code, so we'll show it to you. Okay. Well, this is the second time I recorded this because the first time the text was so small you couldn't see it. So I got this in Play-Doh mode now. Hopefully you'll be able to read it. But here's my wood stove controller module. I got 3 libraries here. First one is for the Max 31855 thermocouple amplifier, which is up in the stack. Second one is the Herculex library, which has been heavily modified to get rid of that software serial crap. And that's to talk to the damper motor. And the PID library, which I modified as well, to talk to the draft motor. First start off with my constants. I have limits for counts and things like that for damper and draft motors. These here are timers that determine when functions get run. These are temperature constants that determine what the stove runs at. For example, if I want to heat something, if I want to heat the room up, the stove can get up to 800. Want to cool it down, I can go as low as 450. Anything lower than 450, I started seeing creosoting problems. So, and what happens is the target is linearly interpolated between these two values. If it gets up to 900 for some reason, if there's a leak in the stove or a crack in the glass or whatever, it'll shut down. This overshoot temperature is for, it does tend to sometimes overshoot, especially when you first put new wood in there. So normally I run the damper at about 80%, but if it gets 50 degrees above my target, I'll close it all the way, which will cut the draft down and cool the stove down a little bit. These values here, this value here is, it will start to close the damper when the stove is above 250. So when it's below 250, it's wide open. There are 4 modes that this can run in. Run mode is the standard thing, which it's doing right now. Load mode is when I want to put more wood in there and open the door. Hold mode is if it's running from a cold start, I hold everything open until it gets going up to 500. Where is it? Holding temperature 500. That's just to make sure everything gets going. And idle mode is if it's you know, basically down to coals, and there's no real value to the heat coming out of it, I'll throw it in idle mode, which will try to keep the coals going as long as possible so I don't have to start from a cold start. These are failure values. These get concatenated onto the end of the status word. So, you know, I'm checking for damper position and status, draft position, thermocouples and stack values, these kind of things. And these are some of the parameters that tell me when to set those bits. You know, this is just basically like hardware stuff. How long it takes the servo, the maximum amount of time it would take the servo to move from one end to the other. These are PID parameters for the draft servo PID loop. You can basically see that it's a PD loop. The I term is almost negligible. Took me a while to figure that out. There's just a little bit of I in there to minimize the offset when it's stable, but you know, the gain is pretty low and the derivative term is pretty low. Here I'm sampling at once a second, so even though the thermocouple and all that stuff is being sampled much faster than that, I'm only really adjusting the servo position at a 1 Hz rate, which is plenty fast enough, and it keeps the servo motor from beating itself to death. So now these tokens, these are all having to do with data that comes from the remote. Oops. They are how I determine what value goes in what RAM position, which I'll show you down the line here. This next stuff is just hardware pin definitions. Here's the memory. I've got some flags. Show what mode it's in. Show whether there's something in the string buffer. Show whether it's in load mode or if the remote is actually polling us. You know, this is, I'm not going to go through all this stuff, but what I'll say about this is I save all the old valid stuff. So in other words, if I get a command word from the remote and it's bogus, I still have the old one that wasn't bogus. So you know, I save, you know, all the important stuff. I'll save it as old from the previous frame that was determined to be good. This part here was primarily done for debugging purposes. This allows me to set the PID parameters from the remote without having to reprogram the control end of things. You know, you gotta screw with these parameters all over the place. It depends on, you know, your stove dynamics, and you know, these numbers that I came up with, it took me a while to come up with them. So, you know, it's going to require some mechanism for tuning the PID loop. These are the timer, the actual timers themselves, which determine when the functions get run. Here we got set up for libraries. I got the thermocouple amplifier. Oops, stuck a breakpoint in there. And the draft PID loop. This takes a stove stack temperature as one of the arguments and comes out with the draft servo command, so it's comparing to the desired target temperature and, you know, computing what the servo should do. Here's just some setup stuff. Serial 1 is the XB for communications between the remote and the controller itself. The Herculex is on serial 2, which is the the damper motor. Here I just initialize it, get it going. This one right here, this sets the PWM up from the Arduino default of like 420 hertz to as close as I could get to a kilohertz, because the draft motor wants to see a kilohertz PWM. So 980 luckily was close enough. You know, pin modes, standard stuff. Down here is where if I'm cold starting this thing, I will cycle the motors just to make sure they're working. And I'll also broadcast back to the remote what PID parameters I'm using. This here I'll learn the draft servo. The feedback from the draft servo is analog and does not track the PWM values, so you have to learn it. I'll get into that later. And then this just has to do with mapping the stove temperature to the room temperature. The main loop here, first thing I do is check to see whether somebody's pressing the load button. If they are, I go into load mode, which allows me to open the door by opening the damper all the way so I don't get a face full of smoke. This routine right here, or this little section of code right here, determines when the timer is expired and puts it back into the last previous mode from when the load mode was entered. This is the detokenizer. This basically gets what the remote is sending if it's there. The way it works is there's a token value that comes over, and then there's a value itself, a float value that comes over. So when it sees a token value, it knows the next one is going to be the one that it stuffs into the RAM location. So if there's something in the buffer, then this part of the code will execute. If not, it will skip it. This is where I determine what the mode of operation is, and if the commands are valid. This part here is some sanity checks to make sure that the data coming from the remote is valid. Sometimes you can get a hit, and it operates at 2.4 gigahertz, and I've seen some kind of crazy junk happen when I'm using my cordless phone, which operates at the same. It's doing frequency hopping spread spectrum at 2.5 gigahertz, so it can clobber the remote link sometimes, so I have that. This part here determines whether we're being pulled by the remote, and if so, sets a flag saying if it's present or not. This part here reads the thermocouple amplifier and the junction temperature, which serves as my local temperature for standalone mode. This determines hold mode, whether we exit it or not. If it's warm enough, it'll exit hold mode and start controlling the stove. Here's where if the remote is not present, I will stuff in the default values. Okay, this part here is the main part of the loop, which calls all the functions, and basically I use timers for everything, so I don't have to put delays in this loop. So this loop will fly through here until it determines that it's time to run one of these functions, and then it does. So the first thing I do is I check the thermocouple. Next thing I do is I check the stack temperature to see if it's out of range. And then if those two are okay, well, even if they're not, but I'll calculate a new target value. This routine here is a stepping routine. A stove can't react instantaneously to changes in the temperature from the remote, so I have to step the parameters to keep everything happy. This part will set the or this function will set the motor positions to achieve the target temperature. And then these two routines here will get the feedback positions for the various motors. And then this routine right here will set the LED on the damper motor. When I'm not, when I don't have the remote going, I can still look at the damper LED and tell what's going on. If it's red, there's a failure. If it's yellow, it's in hold mode, which means it's warming up. If it's pink, it's in load mode, which means I can open the door. If it's cyan, it means the remote is not talking to the controller. And if the LED is off, it means it is talking to the controller. This part here, it gets the draft position, reads an analog feedback off of A0, and I have a guard. I don't set the motor to its extremes. I have a 15 count guard band on each end, so if the feedback goes past that guard, I know that there's something wrong with the motor. If it jams or something like that happens, if it fails, the motor will set the feedback to either 0 or full scale, which I guess is a feature of that motor. I can tell at that point that there's a failure thing. If any of these failure bits get set, it stops controlling the stove. So I set the failure bit if there's a problem. And this here, it just maps the position to a percentage that I can display on the remote. Like I said, they all run off the millis timer. Same thing, damper feedback. I can get the position. I can get the status. I map the position to a percentage. If there's any problems, I set the failure bits. Now, sometimes, being next to a hot wood stove, I'm not exactly sure why, but they create electrical noise. And these are not LVDS signals coming back and forth. So every once in a while you will get a COM error. I don't want to fail with a COM error because I'm pulling this thing pretty quick, once every half a second or something like that. So if there truly is a failure, like a wire breaks or the motor, loses its marbles, I'll get, a ton of errors. And, when I exceed a count, I think it's 50, I'll determine that that is a hard failure. But if I get the occasional COM error from, electrical noise, it pretty much will ride through it. So I do that on both that and the thermocouple. The thermocouple has some pretty horrendous noise on it because it's like basically right in the flame. And I'm not exactly sure, but it's capacitively coupled to the flue. It's an insulated thermocouple, but capacitively there can be noise induced on the junction, which can cause sporadic errors. So I do that. Now we're getting into the function calls of, setting stuff up. This is how I set the new PID parameters if I send them from the remote. This one here, this will check the thermocouple, and same thing, if I get more than a bunch of errors in a row, I'll set a failure bit. If I stop getting errors, I'll clear it. There's also a function in the library that it'll send not a number if it can't read the thermocouple, and so I take advantage of that. If I'm getting garbage, from comms with it, I think it talks on the SPI bus, then I'll set the failure. I'll determine that there's a problem with the comms for the thermocouple. Any of these, the thermocouple, the stack temperature, any of these can safe the stove. So same thing here, you know, I check the value to see if it's too hot or too cold. If it is, I will safe the system, you know, to keep it from going crazy. Let's see. Okay, here's where we calculate a target. I calculate a set point error based on remote ambient temperature and remote set point. You subtract the two, you get the delta, and then you can map that between. This is the gain of the whole system here, and this is what I was talking about with the heating target bound and the cooling target bound. You know, the way my system is set up with this mapping, the way it is now, is 1 degree of room temperature equals 50 degrees of stove temperature, stack temperature. So, you know, it depends on all sorts of stuff. It depends on your house. It depends on your stove. You know, you just got to futz around with that until you get it to the point where it'll close the loop good. This routine here is where I step the parameters. I mean, once I calculate a target temperature, I'll walk it at a certain rate, up or down, and this does this to keep the, you know, to allow the stove to catch up. You know, for other words, if I'm running this thing without the remote control and it's running at defaults, and then all of a sudden I turn on the remote control and it steps the ambient temperature by like 10 degrees or whatever, you know, stove can't handle that. So it'll step these temperature values at a rate that the stove can follow. And again, that was done, you know, experimentally. Here comes the damper servo command. I stepped that as well because it can get noisy if it starts flopping around all over the place, and there's really no need to have the damper moving very fast. So, you know, I stepped the damper command just to, you know, keep things quiet and, you know, keep the motor alive. So let's see, what else do we have here? Stove controlling, here we go. This will use the PID loop to control the draft motor. Here's where I stuff in a default value if the remote is not present. And once the PID loop has computed the value, I write it out to the servo. The damper motor is a little different. I implement a dead zone so the thing isn't like tracking all over the place like crazy. It doesn't need to. So, you know, I do that, and, you know, once I figure out, okay, I map the target temperature to, you know, where the damper servo position was, and come up with a value that's the new damper servo command. I save the old one, and, you know, the step routine will move it at a slow rate, so it's nice and quiet. Here's where I learned the draft servo feedbacks. You know, I set it to the max, I wait some time, I read the feedback, I set it to the min, I wait some time, I read the feedback. This routine gets executed at the start of this, you know, in a cold start. It also gets executed when I do a load mode, because the draft servo does have a long-term drift associated with it on the feedback. I've noticed, like, if I keep the thing going for a week or so, once in a while I'll start getting sporadic feedback failures, and it's because the feedback has drifted. It's analog. I think it's basically a linear pot inside of there. And, you know, it's sitting right next to a red hot stove, so it does drift around a bit. So every time I throw new wood in there, I learn the feedback. Here are the modes. Load mode. Basically, load mode just sets minimum damper. You know, sets the status and stuff like that to tell the system what's going on. Hold mode Same thing, holds everything wide open, the damper and the draft, until it heats up. Idle mode. This is once the stove starts running out of gas, it'll set the damper and the draft to 80%, which is enough to keep them going, but not roaring. Hopefully they'll last a longer time that way. This is where I send the status packet back to the remote. Things that I'm sending back. It sends me an ambient temperature, a set point, and a command, and I answer with my ambient temperature at the stove, the stack temperature, the damper servo percentage, the draft servo percentage, status word with the mode on the top byte, and the failure bits on the bottom byte, the target temperature that it's calculating and trying to achieve, and this here is a debug parameter. It could be anything, any RAM location in the thing. It just allows me to see what the controller is doing at the remote, because I don't have a computer over by the wood stove. This is a linear interpolation. What is it? Arduino only has the integer version of this. I wrote a float version of it because all these values I'm computing are floats. And then this is the event handler for the serial interrupt on the XB. Basically what it does is the ISR, when it gets a byte in the input buffer or the input register of the UART, it sticks it into a circular buffer. When I can read it with this function, if it's a 0D, which is a string terminator, I know that that is complete at that point. So I stuff it in, I convert it into a float value, and then stick it in my buffer, my RX byte. And then I set string value to true, which up here at the detokenizer, if string flag is true, I will detokenize that value and process it. The only last little thing here is when I use print line on the remote end of things, it terminates the string with a 0D, which is a carriage return, and a 0A, which is a line feed. Since I don't need the 0A, I ignore it. I just basically flush the buffer. So that's how the code works. It's pretty straightforward. It works good. I haven't had too many problems with it. I will say that it's hard to judge how much wood I've been using from last year when I didn't have this thing going. But, because, you get different wood, you get different temperatures, blah, blah, blah. This thing, I will say that my wood pile, I'm using about half the amount of wood I used last year, given all those other caveats. So it has made a huge improvement in the amount of wood that I'm burning. Typically on a cold night, I would probably throw 15 pieces of wood in there. Now I'm throwing like maybe less than 10, 9, 8, whatever. So that's cool. And the other thing is it's really nice to be able to just get up, throw wood in the thing, and shut the door and not have to futz around with the controls. This thing will, when you put new wood in it, it'll open it wide up till it gets hot. As soon as it gets the right temperature, bang, it starts throttling back, so I don't have to get up and, play with the controls. And that's a huge convenience, especially at night. When you get up 2 in the morning to throw wood in the stove, you don't want to have to sit there for a half an hour until it gets going. I just, shut the door and go back to bed, and this thing just controls it, no problem. So hope you learned something. The usual caveats apply. If you do this and you burn your house down, it's not my fault. You're taking the responsibility for yourself. You know, I will say that my stove is safe, even if you know, I throw a bunch of wood in there and, you know, open it up wide open. Doesn't like burn the house down. I mean, yeah, it gets uncomfortably hot. I mean, I've seen that temperature up as high as 1100 degrees on the stack, which is probably not too good. But you know, depends on what you got for stove, I guess. You know, some stoves, if you open them wide open and you throw wood in there, they could overfire and do some damage. But you know, doing this at your own risk. Hope you learned something. Thanks for watching.